Okay, so we're going to work on problems out of chapter 21 today, which has to do with electric potential. And it is covering both potential energy, and then also capacitance. So you've got all of those things covered in this single chapter. So remember we said last time that capacitance was, or excuse me, that potential and potential energy were sort of the cousins to electric field and electric force, because we're going to see that the formulas look similar, but the problem is, or not the problem, they are similar enough to be confusing, but they are very different things. They are both scalars, which means you have to use the sign of the charge in the calculation. You can't just use the magnitude. There is no vector picture to draw, and you don't have to do component method of addition, which is nice. So that makes our life a little bit easier. We're just basically adding up numbers, okay? And so that makes it a little bit easier. The trick is to make sure that we are adding up the correct numbers by using the sign of the charge, okay? So we're going to practice a few of those today. All right, so we'll start with problem number 21, and you'll see why I skipped over to that one, because that begins just initially talking about potential, and that's the first topic that we discovered. Kat, go do that somewhere else so you're not shaking the camera. All right, okay, so in problem 21, it says what is the electric potential at the point indicated by the dot in figure 2121. So let me draw that figure for you, okay? So what we've got is we've got 3 positive charges arranged in a little bit of a rectangle here. They are all 2 nanocoulomb charges. And this distance here is 3 centimeters, and this distance here is 4 centimeters, okay? Okay, y'all don't want nothing to do with me until it's time for me to teach class, and then everybody wants to get up here on the table. Get down. Okay. So I want to find the potential at this point down here. Now, just like with the field, you don't need a charge here for there to be potential. The potential of this charge configuration exists all the time, even when there is not a charge here to feel some sort of potential energy. It's sort of the complement of potential energy and force go together. So if I wanted to calculate that, I would need a charge here. But if I just want to calculate V, then I don't need a charge there. Okay, so I know that V for a point charge is K Q over R. Now notice there's no magnitude sign here, and there's no squared on that R. So what I need to do is I need to find R. So the way I do this is for V, since it's a scalar, V total is just V1 plus V2 plus V3, and you just add up 3 numbers. That's it. There's no X's and Y's, there's no sines and cosines, there's none of that. Okay, but I need to figure out what the R values are. So let's number these charges. Let's call this one 1, this one 2, and this one 3. Okay, so R1 is going to be that distance right there. R2 is going to be that distance right there. And R3 is going to be that distance right there. Okay, so these two are pretty easy to figure out, because this one's just going to be 3 centimeters and this one's just going to be 4 centimeters. But I have to use a little bit of trigonometry to find R1. Well, since this is a right angle, I can use Pythagorean theorem and figure out R1. And I happen to know that R1 is 5 centimeters. Okay, that's 5, centimeters, not 50. So that's 5 centimeters. Okay, so when I get ready to calculate my values, then what I do is I simply just add them up. Now, these are all positive charges, so I don't have to worry about keeping track of any negative signs. Okay, so this is going to be K Q1 over R1 plus K Q2 over R2 plus K Q3 over R3. It's just that simple, okay? So K, we know Q1, Q2, and Q3 are all 2 nanocoulombs. I don't like nano, remember, so I'm going to go ahead and write that out as 2 times 10 to the minus 9 over R1, which we know from our picture is 5, right here. So that's 5 centimeters, so that's 5 times 10 to the minus 2 meters. I don't like centimeters either. Okay, then K Q2 is also 2 nanocoulombs. So I write that out over R2, which was 4 centimeters. And then K times, again, 2 nanocoulombs over R3, which was 3 centimeters. Okay. K, remember, is 8.99 times 10 to the 9th. That's just that constant like we used in the last chapter. So that's 8.99 times 10 to the 9th, 10 to the 9th Newton meter squared per coulomb squared. That's the same K we used in the previous unit. So we literally just add up those numbers. Very simple. There's no components. There's none of that. So you just add them up and you get V. Okay, now, the only difference would be, let's say one of these was negative. Let's say number 3 here was negative. So all I would do to change this is I would just put a minus 2 times 10 to the minus 9 coulombs in here. So this term would be negative, okay? So potential is actually easy to calculate if you remember that it's a scalar and you remember the formula for the point charge potential, which is right there. So you just add them up. Okay, nothing too tricky. So this was problem number, I forgot to write that down. This was problem number 21. Okay, so it's a scalar, so you just add them up. Okay, all right, let's do another one. Okay, let's see, find one that's maybe got a negative charge in it. Let's do problem 72. It's going to look a lot like this, but it's got a negative charge in it. So that'll be a good one to practice on. Okay, so it says 72 says, what is the electric potential at point A in the figure? And then it wants me to find the potential energy of a proton at point A. All right, so this will be a good next step problem here. So this is 72. I'm going to draw my picture again. So I've got this fall. It looks a lot like the picture we just had. This one is 10 nanocoulombs, and this one is 5 nanocoulombs. And then I've got this one, which is negative, and this one is minus 5 nanocoulombs. Okay. This distance here is 2 centimeters. This is 4. And my point A is right here. All right, so it looks a lot like the picture we just had, just some of the different sizes are different, and then we've got a negative charge. So the first part says, what is the electric potential in point A? So it's just like what we did. I want to find the potential at point A. So let's number these again, 1, 2, and 3. Okay, so it's going to be just like what I had. V at A is equal to V1 plus V2 plus V3. Okay. So I need to find my R's again. So there's R3, there's R2, and there's R1. So R3 is 2, R2 is 4, but R1 is going to be whatever 2 squared plus 4 squared is. That's going to be the square root of 20. So whatever that is, you can figure that out. Okay, because I used Pythagorean theorem to find R1. Okay, so it's 4, 2 squared is 4, and then 4 squared is 16, so that's 20, so it's square root of 20. You can find that number with your calculator. Okay, all right, so I'm going to do the same thing I just did. So it's K Q1 over R1 plus K Q2 over R2 plus K Q3 over R3. Okay, just like I did, except now, it's not K1, it's just K. So K Q1, if I remember from my picture, is 10 nanocoulombs. So 10 times 10 to the minus 9 coulombs over R1, if I remember from my pictures, whatever the square root of 20 is, you can figure that out with your calculator. But it's times 10 to the minus 2 because I don't like meters. Okay, plus K Q2 is the minus 5. So now I need to put in negative 5 times 10 to the minus 9 coulombs. So this term is going to be negative. I must remember to put that negative in. Then R2 is easy because it's just 4 centimeters. So 4 times 10 to the minus 2 plus K times R or Q3, which was, I put 5 centimeters. That should be 5. That should be nanocoulombs, sorry, nanocoulombs. So 5 nanocoulombs. So 5 times 10 to the negative 9 coulombs over R3, which is 2 times 10 to the negative 2 meters. Okay. And then I just put in what K is. Again, we know that K is 8.99 times 10 to the 9th Newton meter squared per coulomb squared. So I just plug in a bunch of numbers again. The only difference is this term right here is going to be negative, but I just add them up. So nothing tricky there. And I get a value for V. Okay. Now, B wants to know the potential energy of a proton at point A. So a proton has a charge of 1.6 times 10 to the minus 19 coulombs because it's the same as the charge of an electron. It's just positive. Okay. And I expect y'all to know that. All right. So then potential energy is just Q times V. Well, I just found V right here. I know Q. So the potential energy is just 1.6 times 10 to the minus 19 coulombs times whatever I get when I add that up. Okay? So you just multiply those out. If I had not done part A, what I would do is I would add up the potential energies of the proton paired up with the other 3 charges. So the way, if I had not done part A, what I could do is I could say it's U of the proton in 1 plus U of the proton in 2 plus U of the proton in 3, right? And then I would use the formula that said it was K Q of the proton Q1 over the distance between the proton and 1 plus Q proton Q2 over RP2 plus K Q proton Q3 over RP3. So if I had not done part A, this is what I would do, okay? But that's because if I factor out the proton charge, I get exactly the same math as I had right here, okay? So if I don't do the potential first, I can use the potential energy formula to find it. So this is an alternate method of solving for it, but you've already done the work, so why not just use the work you've already done? The only difference here is the only thing I would need to remember is remembering Q2 is negative, so this term would be negative, okay? So if you had not found part A, this is what you would do, all right? But since we already did most of this work already, we just need to multiply by the charge of the proton here to get the total potential energy, okay? Remember, potential is in the units of volts, or you can abbreviate that with a V. And I know it's confusing because I've got a V for potential and a V for volts. So I'll usually put a little hat on my volts V. And remember, this potential energy, when you calculate, it's in joules or J. Okay? All right. So that was problem number 72. All right, let's do another one. Let's do problem number 9. Okay, problem number 9 says, what is the potential difference needed to accelerate a helium plus ion from rest to a speed of 1 × 10⁶ meters per second? Okay, so this is problem number 9. Now they tell me it's a helium plus ion. So they tell me that its charge is +1 electron. So that's 1.6 × 10⁻⁹ coulombs. Oops, 19 coulombs. Okay, because I've got a deficit of 1 electron, so it makes it a +1 charge. Then they tell me that its mass is 4 times the atomic mass unit. And I can look that up. Okay, it's in my book, or you can look it up on the internet if you really want to. But you can look it up in your book and it'll tell you what the U mass is, okay? So it's in the front cover or the back cover, it's somewhere around in your book if you don't remember what it is. So you can look it up. All right, now, so you know the mass. Now, here we've got a situation where it says, what is the potential difference needed to accelerate a helium ion from rest to a speed of that? So what I've got is I'm thinking about an initial position where it's at rest and a final position where it's got maximum kinetic energy. Okay? So I know at this point right here, U is a max and K is 0. And over here, I know that K is a max and U is 0. So I'm converting all my electric potential energy I have here into kinetic energy here. Okay, so the way this works is U initial plus K initial equals U final plus K final. All right, I know that that's 0. Now I'm going to do something a little bit different here. I'm going to say K final is equal to, and I'm going to leave this as U final minus U initial, or excuse me, U initial minus U final. Okay. But then remember, U is Q V initial minus Q V final. All right. And if I factor Q out, this thing right here is what I call the potential difference. Remember in the notes, if you've looked at them, we had that thing called the potential difference. Okay, which they've told me in the problem. They told me, or they want me to find it. So this is the thing I'm actually solving for. So sometimes you'll see this written as Q delta V like that. Okay, and this is what I want to solve for. Okay, all right. So I know a couple of things. I know the final speed is 1.0 times 10⁶ meters per second. Okay. I know the final speed that was given in the problem. I know the mass and I know Q. So I'm going to rearrange this to solve for potential difference. So if I do that, I have to remember what K is. So I've got 1/2 mv squared final is equal to Q delta V. So delta V is just going to be 1/2 mv final squared divided by Q. And I think I know all that stuff. I know what M is because it's a proton and I can calculate 4 times U. I know what V final is because they gave it to me in the problem. And I know what Q is because it told me that in the problem. So all I need to do is multiply all that out and find V. And delta V is going to be measured in volts. So I'm going to put my little hat on it there to tell me what it is in volts. Okay? So it's a conservation of energy problem, just like we would have done in Physics 1. Okay? And yeah, so pretty straightforward. Okay? All right. So they gave me everything I needed there. I don't know why in this book they make this a 4-star problem or whatever, because it's really, I guess because you have to go look up U. And that's hard work, apparently. All right, let's do another one. Okay. Let's look at, problem 16. Okay, problem 16. Okay, actually, I'm going to pause this recording real quick. I have a dog that wants out, so I'll be right back. Okay, all righty. So with problem 16, says I've got a 2 centimeter by 2 centimeter parallel plate capacitor. Okay. So I've got 2 plates that are separated like so. Well, that's terrible. Let me try that again. Drawing things is not my strong suit. So they look something like that. All right. So there's 2 plates and they're 2 by 2. So I'll just draw a side view of them because I can do that. So this is 2 centimeters by 2 centimeters. Okay. And they're separated by, do they tell me? Let's see. Has a 2 millimeter spacing. So the separation of the plates is 2 millimeters. And I don't like millimeters. So I'm just going to start right off the bat by turning that into meters. And I'm going to start and do these as 2 meters also. 2 times 10 to the minus 2 meters. So get everything in meters. All right. It says the electric field strength inside the capacitor is 1 times 10 to the 5th volts per meter. So I know that E is 1 times 10 to the 5th volts per meter. Okay. And it says, what is the potential difference across the capacitor? So there's a simple formula for the capacitor. It said that V was equal to E times D, where E is the electric field and D is the spacing. So very straightforward. V is equal to just 1 times 10 to the 5th volts per meter. Put my little hat on volts. Times the spacing, which is 2 times 10 to the negative 3 meters. And I just multiply those two together and I get my voltage. So that's pretty easy to figure out. That's 2 times 10 to the 2 volts. So 200 volts. Okay. All right. So they told me the electric field. They told me the spacing. So it's very simple if I remember this little formula for a capacitor. Then it says how much charge is on each plate. Okay. So I have to remember the definition of capacitance, and I have to remember how to write down what a parallel plate capacitor is. So I know the definition of capacitance is C is equal to Q over V. Okay. I want to find the charge on the plate. That's the thing I'm solving for. Okay. I know this. I just calculated it in part A. But I also need to find this. I need to find the capacitance. So I have a formula for the capacitance of a parallel plate capacitor that says the capacitance of a parallel plate capacitor is epsilon naught, which is that constant, the permittivity of free space. I looked that up, times A over D, where A is the area of the plate. And then in this case, that's pretty easy because it's a square. So it's just the length of a side squared. Okay. So remember, they told us that. So this is the length of a side. These are both squares, or this is a square. So I know that. I know the spacing. They told me that also. So I know that. Okay. So I can very quickly solve for the spacing, or excuse me, the capacitance of the capacitor. So the area is just going to be 2 times 10 to the minus 2 squared. Okay. And I know D is 2 times 10 to the negative 3 meters. And epsilon naught, I look up because it's in the front cover of my book. Epsilon naught is the permittivity constant, and it is 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. Okay, so I find the capacitance. I use epsilon naught A over D, and I find the capacitance. Once I know the capacitance, then Q is just C times V. So I know V from part A. I just calculated C, so I just multiply those two things together, and that gives me Q. And remember, charge is in coulombs, or C. Okay? All right. So I think that was all that problem asked me. Yes, how much charge is on each plate. Okay? All right, so that leads us into talking a little bit about capacitors. And so let's do a couple of capacitance problems. Okay, so it says, let's see. All right, let's look at problem number 38 because it's kind of fun. All right. 38 says, we've seen that bees develop a positive charge as they fly through the air. When a bee lands on a flower, charge is transferred and an opposite charge is induced in the earth below the flower. The flower and the ground together make a capacitor. A typical value is 0.8 picofarads. So the capacitance is 0.8 picofarads. And if I don't remember what pico is, the front cover of my book reminds me that's 10 to the negative 12 farads. Okay. It says if a flower is charged to 30 volts relative to the ground, bees can reliably detect the added charge and then avoids the flower in favor of flowers that have not been visited. So basically this is a tag to tell them that a bee has already been there and gathered the pollen. All right. Approximately how much charge must a bee transfer to the flower to create a 30 volt potential difference? So the potential difference is 30 volts. So they're wanting me again to use the capacitance definitions, Q over V. So I want to find again the amount of charge. So Q is equal to C times V. And I know both of those. So I just simply plug in those numbers. Like so. And I multiply them out and I've got my answer. Okay, that says how much charge. Now, if they had asked you for the number of electrons or something, then you would just divide your total charge by the charge of one electron, and that would give you the number that you needed there. They don't ask that here, but they might. Okay. All right, so let's go on and do another one. Let's look at problem number 47. Okay, 47. It says a 25 picofarad parallel plate capacitor, so 25 times 10 to the minus 12 farads, because it's picofarads, with an air gap between the plates is connected to a 100 volt battery. So initially, the initial capacitance is that. I have an air gap, which tells me that there's no dielectric in there, and the voltage is connected to a 100 volt battery. A Teflon slab is then inserted between the plates and completely fills the gap. What is the change in charge on the positive plate when the Teflon slab is inserted? So I put in a Teflon dielectric. Now, it says I'm hooked up to a battery. So that tells me that V is a constant. Okay? If I stay hooked up to a battery, I have whatever voltage I have because that's determined by the battery. If I'm charged and then removed from the battery, what stays charged or what stays constant is charge, like you saw in the notes. Here it says I'm going to stay hooked up to this battery. So V is going to be a constant, all right? So the first thing I need to do is I need to find C, the new C, which is my dielectric constant kappa times my old capacitance. So I have to look up for Teflon. Now, if I had this problem on a test, I would have to give you the number, or I would have to tell you where to look it up at, okay? So your book has a list somewhere of dielectric constants for different materials. And it's in a table, and it's in the chapter. So the table says that the dielectric constant for kappa is 2. Okay, so this is just 2 times my old capacitance, so that's pretty easy. So that's just 50 picofarads. Okay, so now the charge on the plates then is, we're going to go all the way, we're going to go back and use the definition of capacitance again. Okay, so they want me to find the change in charge on the plates. So I need to find Q original, okay, and that's going to be C original times V, which is going to be 25 times 10 to the minus 12 farads times 100 volts. And they want me to find Q final, which is the new capacitance, times V, which is now 50. This is pretty easy to figure out, but we'll write it out anyway because it might not be this simple in another problem. And so the change in Q is just going to be Q minus Q initial. Okay? Because it wanted to know the change in charge, not the total charge on the plates. Okay? I want to find the change in charge. There we go. The change in charge. All right. So, yeah, and I knew they told me it was Teflon in the problem. So I had to look up the dielectric constant. That's not something you know off the top of your head. You have to look it up. Okay. All right. Let's do another one. Now, when you talk about capacitors, remember there's different formulas that you can use to calculate the energy, but they really all are the same thing. They're really all the same formula, just rearranged depending on what variable you know. And we talked about that in the notes, okay? So when you look at a problem like problem number 53, you just have to figure out what you're given and figure out which one of those 3 formulas that you need to use to find the energy, okay? So when you're solving for the energy in a capacitor, you just have to figure out what variables you know, and then it's a pretty easy process to figure it out, okay? So when you look at the energy in a capacitor, you had some different formulas. One of them was, and this is for problem 53, one of them was the energy was 1/2 Q times V, okay? And then one of them was also, if you remember from your notes, it was 1/2 Q squared over C, or you had 1/2 CV squared. They all did the same thing. They just had different variables showing up in them. That's Q over C. That didn't look very good. All right. Okay, so in this problem, in problem 53, it said, to what potential should you charge a 1 microfarad capacitor to store 1 joule of energy? So I want to find potential, and they've told me capacitance is 1 microfarad. So again, I don't like micro, so I'm just going to go right ahead and get rid of that. And then they've told me U is 1 joule, okay? So I want the one that relates U to C and V, so I'm going to pick this one, okay? I'm going to pick that one. So I know U is equal to 1/2 CV squared, okay? And then I know this stuff. So U is 1, C is 1 times 10 to the minus 6 farads, and I'm going to solve for V. So if I pick the right formula, it's pretty doggone easy to then get it worked out, okay? So just solve for V, okay? All right. All righty, let's see. I had any other ones picked out that I wanted to look at. I kind of just went through and chose some that were representative of what we've been working on. Okay, so what you should notice from looking at these problems is like this formula or this problem right here looked kind of similar to what we did in the last unit, except, or in the last set of notes, except we didn't have to worry about it being vectors. That's where people get these things messed up. On a test, I might ask you to solve for potential. If you do a vector problem and I ask you to solve for potential, I can't give you any points because that's not the right thing. So you need to make sure when you read the question, you read it carefully and you solve for the thing that I'm asking for. Okay, it'll be very clear on the question. You just have to make sure you solve for the right thing. Okay, so that's all the problems that I had picked out here. So that, unless somebody has a question about one of the ones that I did, that's all we're going to do for today. I'm going to stop the recording and see if anybody has